Hi, my name is Fabien Baradel, and I will present our paper on counterfactual learning of physical dynamics, joint work with Natalia Neverova, Julien Mille, Greg Mori, and Christian Wolff. In this example, it is straightforward for humans to understand what happened. The baby on the right steals the silencer from the other baby, who starts the cry. Humans are also able to anticipate what would happen under a different scenario. For instance, if the silencer were not present in the scene. This concept is called counterfactual reasoning, which deals with a problem containing an if statement, which is untrue or unrealized. In this work, we focus on counterfactual future forecasting of physical systems. Given an observed sequence composed of an initial state and the original outcome, we modify the initial state by moving an object and then ask our system to predict the counterfactual outcome. At the heart of the problem are confounders, which are latent variables, unobservable in a single frame, in our case, masses, gravity, or friction coefficient, but mandatory for making accurate counterfactual prediction. Our task is different from classical feed-forward forecasting of the future, where only the initial state A causes the outcome B. For counterfactual prediction, we assume a confounder variable denoted U, which both affect the present and the future. We observe the sequence A, B, and modify the initial state by setting its realization to a certain value C. This intervention is modeled by the do operator. The prediction of the outcome D can be done from the confounder information inferred from AB and the modified initial state. In the literature, counterfactual learning has been tackled on low-dimensional data so far. So we proposed a new benchmark composed of 3 different datasets involving different dynamic systems. After watching a dynamical system, we ask what the outcome would be if we modify the initial position of a certain object. We provide the intervention for the training procedure, and we ensure that the dataset is highly balanced and close to bias-free, guaranteeing that estimates of the confounder quantities are necessary for making correct predictions. In this respect, our benchmark is different from other benchmarks on intuitive physics such as InVis, FEAR, or Clever. We proposed an object-centric method called CoPhy, which can be decomposed into 3 stages. First, for each image, we extract a 3D object position, and we create a fully kinetic graph over objects. The observed sequence AB can be seen as a space-time graph. A recurrent graph convolutional network extracts one latent embedding for each object, which should encode confounder quantities such as masses or friction coefficient. We insist that we do not supervise the latent embeddings. Given the graph from the modified initial state C and the confounder embedding, we predict object trajectories with autoregressive recurrent graph network. We report a human study on data similar to the block tower dataset. We ask humans to predict the location of each block in counterfactual and non-counterfactual settings and compare against our method. We show that our method outperforms humans' performance by a large margin. We report the performance of our method compared to copying baseline, feed-forward video prediction, and a soft upper bound model that have access to the confounder quantities. Our method reaches performance on par with the soft upper bound approach, indicating an extraction of meaningful confounder information. We also present different studies on generalization to unseen confounder configuration and to unseen number of blocks. More experiments are reported in the paper. In conclusion, we propose to address a new task of counterfactual learning from high-dimensional spaces by introducing a new benchmark and a new method. Our method is able to encode object confounders property into a Latin space without supervising confounder. The dataset and code are online. Thank you.